Hey there, and welcome to this explainer on Chapter 18 of the IT 204 textbook. Today, we're diving deep into industrial flow measurement principles. Now, if you're an instrumentation student or really anyone working with process control systems, you already know the golden rule. It's that classic principle, garbage in, garbage out. If your measurement data is bad, well, your control decisions are going to be bad too. There's just no way around it. So today we're going to unpack the actual physics of fluid flow and look at the real-world industrial technologies we use to capture that data flawlessly. Let's get into it. Okay, here's a quick roadmap for our explainer today. We'll start with an introduction to fluid flow, then look at fluid properties like density and viscosity. After that, predicting flow with the Reynolds number, move into velocity and differential pressure meters, and finally wrap up with ultrasonic and mass flow meters.
All right, Section 1, Introduction to Fluid Flow. Let's establish some foundational building blocks.
So what exactly is flow? Basically, it's just the passage of a quantity of a fluid past a specific point. It sounds super simple, right? Whether it's water rushing through a pipe or air blowing through a massive duct, if a quantity of it is moving past a fixed marker, you have flow. We really have to nail this core idea down before we look at all the complex ways we actually measured in the field. Now, we usually think about this movement in two totally different ways: flow rate versus total flow. Flow rate is your right-now measurement. It's the exact quantity of fluid moving through a channel in a specific, immediate period of time. Total flow, though, that's historical. It's the cumulative total amount of fluid that has moved past that point over a specified time frame. Think about when you're driving your car. Your flow rate is the speedometer telling you exactly how fast you're going right this second, while total flow is your odometer telling you the total distance you've traveled all day. Another really vital distinction here is volumetric versus mass flow rate. Are we measuring the physical space the fluid takes up, or its actual, literal mass? Volumetric flow rate measures volume, think gallons per minute for liquids. But mass flow rate, that measures weight or mass, like pounds per hour. This perfectly illustrates why steam flow in an industrial plant is almost always measured in pounds per hour. Steam can expand and contract wildly based on temperature and pressure, so just measuring the space it takes up doesn't really help us. We need to know exactly how much actual mass of steam is moving through the system to do the work. Moving right along to Section 2, Fluid Properties, specifically density and viscosity. Let's see how the invisible forces of a fluid dictate its behavior. Obviously, density is important, but we're going to focus heavily on viscosity right now. You can basically think of viscosity as a measure of a fluid's thickness. Technically speaking, it's the fluid's resistance to flow, which happens because of the internal friction between fluid layers as they slip past one another. Just imagine trying to pour a jar of thick honey versus a glass of water. The honey has super high internal friction. And just for some context here, water has an absolute viscosity of very nearly 1.000 centipoise, which makes it an absolutely perfect reference point for us. Now, temperature plays a massive role here, but it acts completely differently depending on the state of the matter. In a liquid, viscosity decreases rapidly as temperature goes up. Think about heating up that honey in the microwave. It pours way faster, right? But in a gas, viscosity actually increases when the temperature goes up. Pretty wild, right? But it's true. So when heated, liquids flow more easily, whereas gases actually flow more slowly. This is an absolutely vital principle to remember for process control, because temperature shifts in your pipes are going to fundamentally change how your product flows.
Okay, let's jump into Section 3, Predicting Flow Using the Reynolds Number.
So how do we use these properties to actually predict fluid behavior? We use a sort of mathematical crystal ball known as the Reynolds number. The Reynolds number is a dimensionless parameter that calculates the ratio between a fluid's inertial forces, which is its speed and mass pushing it forward, and its viscous forces, that internal friction trying to slow it all down. Density, velocity, and pipe diameter drive those inertial forces on the top of the equation, while viscosity sits on the bottom as the resistance. The result of this ratio tells us if the flow inside the pipe is going to be smooth and predictable or totally chaotic. When that Reynolds number comes in below 2000, it means the viscous forces are dominant. They act like a strict traffic cop, keeping all the fluid particles perfectly in line. We call this laminar flow. It's a really smooth, straight line kind of motion, which you'll often see in slow-moving or highly viscous fluids. Conversely, if the number is greater than 3500, those inertial forces take over. The fluid is just moving too fast for the internal friction to keep it orderly. This results in turbulent flow, which is full of rapid, irregular, swirling patterns. Now, there is a transitional zone between 2000 and 3500, but above 3500 is pure turbulence. And here's a fun fact. Because of the high velocities required, most nuclear facility fluid systems operate entirely with turbulent flow.
All right, section 4, velocity and differential pressure meters. Now that we've got the physics down, let's look at the hardware. Engineers have a massive, and I mean massive, variety of instruments available to capture this data. It all branches out into completely different categories depending on whether you're measuring in closed pipes or open channels, like a wastewater flume. From there, the tree branches again into total flow meters, which use direct positive displacement, think things like oval gears, and flow rate meters, which include differential pressure meters, magnetic flow meters, and a bunch more. Let's zoom in on one of the most common methods out there. A truly foundational concept in differential pressure measurement is Bernoulli's equation. The idea here is that if a fluid flows through a tube and you artificially decrease the tube's diameter, basically creating a restriction, the fluid has to speed up to get through it. And as that velocity increases, the pressure drops. By measuring that differential pressure, meaning the pressure right before the restriction compared to the lowest pressure right at the restriction, we can mathematically calculate the exact flow rate. The flow rate is actually proportional to the square root of that differential pressure. One really fascinating application of Bernoulli's principle is the Annu bar. The Annu bar harnesses this exact physics, but it acts as an averaging pitot tube. It measures liquid, gas, or steam flowing through a pipe by sampling the velocity across the entire width of the pipe, comparing the difference between the total pressure and the static pressure. It's a real game changer because it allows for highly accurate volumetric flow rate calculations without having to cram a massive restriction plate inside your pipe.
And that brings us to our final section, Section 5, ultrasonic and mass flow meters. Let's see how advanced electronics measure flow. Ultrasonic meters are just incredibly versatile. They operate by measuring the transit time of sound waves crossing a pipe. And the best part, because they often just clamp right onto the outside of the pipe, they don't obstruct the flow at all. They can measure everything from large factory conduits and thick industrial slurries all the way to literal massive open ocean currents. They just transmit high-frequency sound through the moving liquid. Basically, if the fluid can transmit sound, an ultrasonic meter can usually measure it. But what about when we absolutely must know the exact weight of the fluid, like in precise chemical batching, when we need to measure the actual mass passing a point per unit time, not just the volume? Engineers rely on inertial mass flow meters. The real heavy hitter in this category is the Coriolis mass flow meter. It uses a vibrating U-shaped tube that physically twists due to the Coriolis effect as fluid pushes through it. By measuring that exact twist, it gives us a direct, highly accurate measurement of mass flow and density, completely regardless of temperature or pressure changes. There are also thermal mass meters that use heat dispersion, plus impeller and twin turbine styles for different applications. Wow, so we have covered a massive journey in this explainer today, from the fundamental physics of viscosity and the Reynolds number, all the way up to advanced measurement tools like the Annu and Coriolis meters. But before we wrap up, I want to leave you with a question. Knowing that bad measurement data ultimately leads to bad control decisions, how will you apply these flow principles to ensure perfect garbage out prevention in your own industrial systems? It's definitely something to think about. If you want to test your knowledge on this IT 204 Chapter 18 material, be sure to check out the study guide or take the practice quiz. Thanks for hanging out with me, keep measuring accurately, and I'll catch you in the next one.